The topic of this video is highway networks. This video was produced in Korean and translated into English. My voice is AI-generated text-to-speech. Let's take a look at the table of contents. First, let's briefly look at the paper that proposed highway networks. Let's look at the structure of the highway networks. And let's compare the performance of the plain neural networks and the highway networks presented in the paper. Next, let's implement a neural network model with highway networks using Keras. Finally, let's look at residual connections, similar to highway networks. The highway network itself is not widely used nowadays. However, skip connections or residual connections, which have the same core idea, are widely used to train deeper networks. In 2015, Rupesh Kumar Srivastava et al. Proposed highway networks in this paper. The depth of neural networks is a crucial ingredient for their success. However, network training becomes more difficult with increasing depth, and training of very deep networks remains an open problem. They introduced a new architecture designed to ease gradient-based training of very deep networks. The authors of the paper proposed highway networks that allow unimpeded information flow across multiple layers of the information highways. During forward propagation, the input signals flow to the upper layers via the highways. Additionally, during backpropagation, gradients flow through the highways to the lower layers. Let's look at the structure of the highway networks presented in the paper. As shown in the figure, there are lower and upper layers. Each layer is a highway network. X is the input of this layer, and Y is the output of this layer. The highway network consists of gates, and there are three weight matrices, WAT and WC. They are all n by k matrices. N is the dimension of the input to this layer, and k is the dimension of the output. The dimensionality of x, y, h, t, and c must be the same. This is necessary for all these operations to work. They are determined through learning. H represents the hidden layer of the plain network. T represents the transform gate, and C represents the carry gate. And the red paths are shortcut connections. The input X can be passed to the upper layer through this path without passing through any parameters. Input data X is fed into three gates. The outputs of the gates are H, T, and C respectively. H is an activation function applied to the dot product of X and WH. The biases are also added. The same goes for T and C. Here H and T are multiplied. And here C and X are multiplied. And here they are added together. This is Y, the output of this layer. If Y is expressed as a formula, it is as follows. Y is fed into the upper layer, and the same process is performed in the upper highway network. Assuming C is 1 minus T, we can simplify it as shown in the figure on the right. Remove the carry gate and multiply X by 1 minus T. Then the output Y will be like this. If T is 0, 100% of the input signal X is passed on to the upper layer. And if T is 1, X is multiplied by 0, so the shortcut connection is closed. And only H is passed to the upper layer, just like the plain feedforward network. This is the T-weighted average of X and H. If T is 0.5, 50% of X and 50% of H are combined and passed to the upper layer. The paper explains that the highway networks were inspired by LSTM, which is proposed by Hochreiter and Schmidhuber in 1995. T is a kind of weight of weighted average, and it uses the sigmoid activation function to make the output be between 0 and 1. Next, let's look at the performance of the highway networks presented in the paper. The figure below compares the performance of plane networks and highway networks of various depths. The x-axis is the number of iterations, and the y-axis is the error. When the depth is 10, the error of the plane networks is smaller than that of the highway networks. That is, the performance of the plane networks is better. When the depth is 20, the error of the plane network increases, while the error of the highway networks decreases. That is, the performance of the highway networks is better. When the depth is 50 and 100, the error of the plane network increases more and more, while the error of the highway networks does not increase. Therefore, we can see that as the network depth increases, the performance of the highway networks gets better and better. Next, let's implement a neural network model with highway networks using Keras. Let's write a code to classify MNIST images. Read the saved MNIST dataset. Split the dataset into the training and test data. Now, let's write a function to implement highway networks. X is the input data, and n layers is the number of highway network layers. Build n layers highway networks. First, we create an H-gate using Keras' dense layer. H-gate contains weights and biases. Since H acts as a hidden layer in a plane neural network, we use the ReLU activation function. Since the activation function is ReLU, we used Kaiming-He initializer for weights initialization. And we initialize the bias to 0. Next, we create a T-gate using Keras' dense layer. T-gate also contains weights and biases. Since T must be a value between 0 and 1, to act as the weights of the weighted average, we used the sigmoid activation function. Since the activation function is sigmoid, we used Xavier-Glorot initializer for weights initialization. And we initialize the bias to 0. Feed X into both H and T gates. Finally, we compute the output of this highway network. So far, a single highway network has been built. We repeat this to build n layers highway networks. The output of the lower highway network becomes the input of the upper network. At the end of the iteration, X is returned. Then X becomes the final output of the highway networks. Now let's build a neural network model with highway networks. Create an input layer. Then we create a 20-layered highway network and feed X input. Create an output layer. Since the target data of MNIST consists of 10 categories, the softmax activation function is used for multi-class classification. Create and compile a model for training. Fit this model to the training data. and observe the history of losses. We measure the accuracy of the test data. Finally, let's check out some misclassified images. Let's check the results. Losses are decreasing significantly, and the accuracy of the test data is 0.9827. Let's check the misclassified images. The first image is actually a 4, but it was misclassified as a 2. This image is actually a 4, but it was incorrectly classified as a 9. Let's run this code. The results are as follows. The highway network itself is not widely used nowadays. However, residual connections, which have the same core idea, are widely used. Let's look at examples where residual connections are used. In 2015, Kaiming-Hay et al. Proposed such a residual network. This is a shortcut connection or identity shortcut. This is similar to a shortcut connection in a highway network. The difference is that the input X is passed directly to the upper layer without going through any gates. Unlike highway networks, identity shortcuts have no trainable parameters. When a gated shortcut is closed, i.e. T becomes 1, the layers in highway networks represent non-residual functions. On the contrary, this model always learns residual functions. The identity shortcuts are never closed, and all information is always passed through, with additional residual functions to be learned. The residual network introduced in the paper is as follows. You can see that the input data continues to flow through the residual connections. Residual connections are also used in the transformer network proposed by Ashish Vaswani et al. In 2017. Residual connections are used in the encoder and decoder. The transformer network was developed for natural language processing. We'll look at this in more detail later in the natural language processing tutorial. Input X is passed to this block and this residual connection. Let the output of this block be H, add X and H, and then normalize. Again, these residual connections are a similar idea to shortcut connections in highway networks. So far, we have looked at highway networks,